Welcome to this video on the blueprint of motion. We will explore how the fundamental laws of linear mechanics translate into the three-dimensional world of rotating bodies. In physics, we often start with the point mass ideal, a simplified model that is easy to calculate but only exists in theory. However, real objects have shape, size, and spin. To understand reality, we must move beyond the point mass and view bodies as systems of particles. The rigid body model helps simplify this complexity. We define it as a body with an unchanging shape, where the distance between particles remains constant. While true rigid bodies don't exist, this is the essential mathematical model for studying tops, beams, and planets. How do we bridge linear and rotational motion? We use the center of mass. This concept allows us to track a complex system as if it were a single point mass, extracting pure translational motion from the chaos of rotation. We calculate the center of mass by taking the weighted average of the positions of all particles. For continuous bodies, this involves integration. For objects with high symmetry, the center of mass simply rests at the geometric center. The center of mass moves as if all the system's mass were concentrated there, with all external forces applied to that point. In this way, internal forces cancel out, allowing us to use the equation mass times acceleration equals external force. Extended bodies can have different types of motion. In pure translation, all particles move with the same velocity. In pure rotation, particles are constrained from translating and instead move in circles around a fixed axis. To understand 3D rotation, we use the vector cross product. This mathematical engine defines a new vector that is perpendicular to the plane of the two original vectors. Importantly, it is non-commutative, meaning the order of operation determines the direction. We determine the direction of this rotation using the right-hand rule. Align your palm with the first vector, curl your fingers toward the second, and your extended thumb points in the direction of the resulting vector. This governs all rotational motion in the universe. We can translate linear kinematics into a rotational world. Just as we use displacement, velocity, and acceleration for linear motion, we use angular counterparts. The two are linked by the cross product of angular velocity and the radius. The cause of rotation is torque. It is not just the force applied, but also the distance of that force from the axis of rotation. Force applied directly at the hinge creates zero torque. Resistance to rotation is called the moment of inertia. While mass measures resistance to linear acceleration, the moment of inertia depends on how mass is distributed. The further mass is from the axis, the harder it is to spin. Consider a solid disk and a hollow ring with the same mass and radius. The hollow ring has a higher moment of inertia because its mass is concentrated further from the axis, making it twice as hard to start or stop spinning. We can reimagine Newton's second law for rotation. Torque equals the moment of inertia times angular acceleration. This mirrors the linear equation, where force equals mass times acceleration. This table acts as the Rosetta Stone of mechanics, showing the direct parallels between the linear and rotational worlds. Understanding these relationships is the key to mastering the physics of motion. Now, let's turn our attention to rotational momentum, represented by the letter L. For a single particle, this is defined as the cross product of position and momentum. For a rigid body rotating on a fixed axis, we express it as the product of the moment of inertia and angular velocity. True mechanical equilibrium requires stability in two dimensions. An object is in equilibrium only if it has no linear or angular acceleration. This means the sum of all external forces must be zero, and the sum of all external torques must also be zero. The law of conservation of angular momentum tells us that if the total external torque on a system is zero, its total angular momentum remains constant. Much like an object in linear motion, a spinning object will maintain its momentum unless acted upon by an external twisting torque. We see this in action through dynamic balance. When an acrobat pulls their arms in while spinning, they decrease their moment of inertia. To keep angular momentum constant, their rotational speed must increase as a result. Ultimately, the physics of rotation reveals the symmetry of the universe. The transition to rigid bodies is a mathematical reflection of linear laws. By mastering these rotational analogs, we unlock the complete blueprint of motion in 3 dimensions.